So I want to keep going with the example that we started in the last video. So I've put up what we've drawn so far for our phase portrait, and I've sort of color-coded. So pink is my X nullclines. That helps out a little bit. The y-axis here is pink. I know with X nullclines, my tangent line is going to be vertical, and it's kind of hard to see little vertical line segments, but it's pink, so I know that they are. Okay, and then purple is my y nullcline, so that's this line here, and the x-axis, and that of course is where our tangent lines are going to be horizontal because y prime is 0. Okay, so last time we had figured out that these were our nullclines, and remember that any time an x nullcline and a y nullcline intersect, we have an equilibrium point. The color coding is actually really nice because that way I can say, ooh, a pink and a purple intersect, it's an equilibrium point. Here, that's two purples intersecting, not an equilibrium point. So I'm going to stick with the color coding going forward. Okay. Now, what I've done is I've shown that the nullclines divide this quadrant up into 1, 2, 3, 4 different regions. And I want to sort of explore what solution curves look like if they start in any of these regions. What I'm going to do is I'm going to start by looking at these nullclines. I know that if I'm on one of the y nullclines, y is not changing. What that means is that my curve at that point is going left or right, but not up or down. So I know from the fact that it's a y nullcline that we're not going up or down, but I can improve on that because I can determine whether we are going left or right. I know we're doing one or the other. Let's figure out which. So I'm going to start with the easiest nullclines, which would be the x and the y-axis. So let's take a look at the x-axis here. So this was a y nullcline, so I know that y prime is 0. If I can figure out the sign of x prime, I can determine whether we're going left or right. So if I look at this interval right here, in between 0 and 2, if I just plugged in 1 for x into the formula for x prime, of course x is positive. This is going to become 4 minus 2 minus 0. That's 2. That's positive. So along this interval, we're going to the right. Now, to the right of 2, let's just plug in 3. Okay. Now, if I plug in 3, I'm actually plugging in the coordinate for this point here, but this point wasn't significant. This was just a place where two y nullclines met. Everything to the right of 2 is going to have the same sign for x prime because this is the only place where x prime is 0 on this line. So if I plugged in 3, I'm going to get positive. 4 minus 6 is negative, minus y is still negative, so I know we're going to the left on this entire segment to the right of that. Okay. Now, what's kind of neat about that is that also tells me that we're going to the left along this line segment right here. Because I know that the only place where my horizontal direction can change is when I hit a y nullcline. So if I'm going to the right here and I happen to bump, well, here I wouldn't bump off of this, but my curves have to be consistent with that. I couldn't have something that was going to the right arbitrarily close to something that was going to the left unless I had a turning point somewhere in there, but my only turning points are on the x nullclines and I don't have one of them. So I don't even have to pick a test point on this part of the line. I can just say, hey, it's connected to two things where we're going to the left, it's going to have to go to the left as well. Okay. All right, so let's take a look now at my x nullcline here. If I look between 0 and 3, and now I'm going to be plugging into y prime because I want to know whether we're going up or down. I know we're not going left or right because x prime is 0. So if I plug in, let's say 0, 1. 1 is positive. 3 minus 0 minus 1 is positive. So here we are going up. Now, I can plug in any point above 3. Doesn't matter whether it's between 0 and 4 or at 4 or above 4, because this isn't a place where it could change. The sign of y prime can only change if I'm at a y nullcline, and I don't have any above here. So let's just plug in 4. that's going to be positive. 3 minus 0, because I'm plugging in 0, 4, minus 4, that's going to be negative, so I know we're coming down along here. Okay. Now, that means we're also coming down along this section here, because it's connected to these other pieces where we're going down. Okay. So let's see what I don't have yet. It looks like I have not yet figured out the sign of things on this line segment or this line segment. But notice those are parts of the boundary of A. And along this part of the boundary of A, we're going to the right. And along this part of the boundary of A, we're going up. And inside of A, there are no places where I can change direction. So we're going to be going up over here as well. Because if we were going down over here, then I'd be somehow, if I'm coming down, then I'd still be coming down a little bit as I came into here. And I can't, because over here, I'm going to be going up. So it's kind of neat. Each region, all of its boundary curves have to either be consistently up or consistently down. And all of its boundary curves have to be either consistently left or consistently right. So same thing up here. Even though this is a ways away from here, these are both boundaries of the region A. In A, it's going to behave like its boundary does. We've got to be going to the right. So notice curves in A will be going up and right. Curves in D will be going up and left. Curves in C will be going left and down. And curves in B will be going down and right. Okay. So now what I'm going to do is I'm going to just draw some possible solution curves starting in each of these 4 regions. And I'm going to try to, if there's more than one possibility, try to figure out what all the possibilities are. So basically, I've got the option of approaching an equilibrium point, because sometimes solution curves do that, or leaving the region to go to an adjacent region. So if I started in A, notice I've got 1, 2, 3, 4. All 4 of my equilibrium points are on the boundary of A. So I could be approaching one of those if I can do it consistent with the arrows. Or I might leave A and go to D if that's possible, consistent with the arrows. Or I might leave A and go to B if that's possible, consistent with the arrows. Okay. So let's just check. If I start somewhere in A, and actually in A, not on the boundary of A. If I start in A, there's no way I can approach this equilibrium point, because that would require me to go down and left, and I have to go up and right. I can't approach this equilibrium point, because while I'd be going right, I'd have to be going down. So maybe I approach this eventually, but not just by staying in A. Okay. Could I approach this equilibrium point? Sure. I could start here and I could come up and right. That's a possibility. I like it. Oops, and I sort of drew this down and right. I meant for that to be going to the right. Okay. Could I approach this equilibrium point? No, because I would have to go to the left, and if I'm in A, I'm going up and right. Okay. So that's one possible behavior. Now, I've just sort of chosen an arbitrary starting point in A. And that's totally fine. I'm just choosing an initial condition, and I'm not drawing it backwards in time. Usually we would do that, where we would draw things backwards in time, but, well, I guess I could. If I went backwards in time, it would just connect up with that. Because if I were actually at a point on here, I'd be going straight up, and I would never come to the right. But I could get arbitrarily close to that equilibrium solution. All right, could I leave A and go into D? Well, let's see. I'd be coming up and to the right. Once I hit here, I've got to go perfectly straight up, and I've got to change my horizontal direction, because if I'm in D, I have to be going to the left. It does look to me like that's possible, that I could do that. I could come, change my horizontal direction. Notice in D, I've got to be going up still, because we were going up along here, but now I'm going to the right, that's basically going to force me to approach that equilibrium solution. I can't cross back into A because if I hit A, I've got to go, if I hit that boundary line, I've got to go up, and that puts me right back into D. Okay, could I cross into B? Looks like I could, because I'm going up and right, and when I hit this, I just go right, and then that's going to force me to start changing and going down. So I would change with a horizontal tangent right here where I'm crossing, then I'm going down and right. That has me approaching that equilibrium point as well. That equilibrium point is looking a little bit like a sink. What we're going to do in our next video is actually linearize all of the equilibrium points and see if we can classify them or not. Sometimes we can, sometimes we can't, we'll see. Okay, so those are the possibilities for if I start in A. Now, if I start in B, let's see. I can't approach this equilibrium point because if I'm in B, I'm going to be to the right of it, and if I'm in B, I'm going left and down. Okay. I can definitely approach this equilibrium point. I see this curve in B does do that. Can I cross into A? No, because if I hit this nullcline, it forces me to the right, it forces me back into B. So it looks like if I'm in B, well, let's see, could I cross into C? No, because if I hit here, I'm coming down, that puts me right back into B. So it looks like if we start in B, we're going to be approaching this point right here. And I can count this tail here as being representative of what happens in B. If I want to draw another representative curve, I certainly could. Okay. Let's take a look at D. So with D, I've got these two equilibrium points. Can't approach that one because I start above it, I can't go down. I've got to be going up and to the right. Can definitely approach this equilibrium point. We saw this curve came into D and then approached that equilibrium point. I can't cross into C because this has me going to the right. And I can't cross into A because if I hit this nullcline, I've got to go up, and that puts me back into D. So pretty much if I'm in D, I'm going to be approaching that equilibrium point. All right, so let's take a look at C. If we're in C, the possibilities would be that I could approach that equilibrium point, or cross into D, or cross into B. Let's see if all of those are actually possible. So if we're in C, we have to be going right and down, because that's what all the boundaries of C are doing. So I can start, say, here and go right and down and approach that equilibrium point. So that's definitely possible. Okay. If I start a little bit lower down and I'm coming right and down, I could cross into D. Now I'm going to have a horizontal tangent here, then we're coming up and left, and of course we'd end up approaching this equilibrium point. So it is possible to cross from C into D. Is it possible to cross from C into B? Absolutely. I know I'm coming down and right. Coming down takes me right into B, and then we determined if we're in B, we're going to have to come down and left to approach this equilibrium solution. So basically, if we're in B or D, we're approaching that equilibrium solution. If we're in A, we can approach that equilibrium solution or cross into either adjacent region. And if we're in C, we can approach that equilibrium solution or cross into either adjacent region. That's a lot of information to get just from knowing where we're allowed to change direction, left, right, and up, down. Okay?